Hello, my differential equation student. I'm happy to meet you again. Today we continue our section 4.4 and finish our section 4.4. Now we have some theorem. And this theorem tells us, theorem number 3, for example, Laplace transformation from function ft over t, it will be integral from s to infinity f sigma d sigma. And equivalently, our function ft is inverse Laplace transformation for function fs, who is t inverse Laplace transformation from integral s to infinity f sigma d sigma. See some example where is this situation we can use this theorem. Example 1. Let's go, we have Laplace transformation from hyperbolic sine t over t. It will be integral from s to infinity Laplace transformation from hyperbolic sine t. Please give me integral from s to infinity. We remember hyperbolic sine t will be 1 over s square minus 1. This means our situation will be d sigma over sigma square minus 1. Here we need separate, use partial fraction. It will be 1/2 integral 1 over sigma minus 1 over sigma plus 1. And sigma is variable when we have integrate. This means the sigma from s to infinity. Each integral it will be natural log, and then we have collect all together. We have natural log 1/2 natural log sigma minus 1 over sigma plus 1. And we need plug s infinity. How we plug in infinity? This means we need found limit, right? Limit natural log sigma minus 1 over sigma plus 1 if sigma approach to infinity. Fraction inside natural log is approach to 1, and natural log from 1 is 0. This means this situation is 0. And my integral will be equal 0 minus 1/2 ln minus 1 over s plus 1 minus put inside like power, and we have natural log 1/2 natural log s plus 1 over s minus 1. You see, this means Laplace transformation from hyperbolic sine t over t is 1/2 natural log s plus 1 over s minus 1. Great. Now we clear and see how we can build some inverse Laplace transformation for some function. And use this theorem. Okay. Let's go. We need counting inverse Laplace transformation from function to s over s square minus 1 square. It will be, use this theorem, it will be t inverse Laplace transformation integral from s to infinity 2 sigma over sigma square minus 1 square d sigma. And here is use u substitution, whereas sigma square minus 1 is u, then it's 2 sigma, d sigma will be du. You can easily evaluate this integral, and it will be t inverse Laplace from minus 1 over sigma square minus 1, whereas you need plugging s and infinity. 1 over infinity is 0. This means if you plug in infinity, it will be 0. And here we have, it will be, this means t times 0 minus inverse Laplace from negative 1 over s square minus 1, or is t, because inverse Laplace transformation is linear, this means minus, you can take it out, and you have inverse from 1 over s square minus 1 will give you t hyperbolic sine t. Now we're ready. Use all our theorem when we study for 4.4 and solving some differential equation. Do some example. I take 2 example from your book. Okay. Number 30. These 2 example help you finish your homework for this section. Okay, I clear all of them. Okay. Number 30, you have t x to the second derivative plus 3t minus 1 x first derivative plus 3x equals 0. And about function, we need found non-trivial solution, and x for 0 equals 0. We don't have value derivative for this initial point, but I think it's enough. Okay. Remember what happened if you have your function multiplied by t. I think I need to remember you. This is our theorem for present before. And we have, if you have Laplace transformation for t f c, it will be minus f prime s. Well, and if you have power c, then it will be something, but here we have only first power. Okay, this means here I need to take a derivative from, what is will be second derivative for x? It will be s square x to the s minus s time value your function who is 0 and minus value your derivative for point 0. And then we need to take it derivative for s, and we have minus in the front. Then we have 3c x prime. This means it will be minus 3 s to the x to the s. Take a derivative, and minus x prime, it will be only minus. Okay, this is I have minus s x to the s, and plus 3x, it will be plus 3x to the s equals 0. Found derivative. X prime from 0 is constant. This means derivative for this part is will be 0. Here we have s squared times x. Use product rule. We have minus 2s x to the s minus s squared x prime to the s. Then we use product rule from s times x. We have minus 3x to the s and minus 3s x prime to the s minus s x to the s, oops, and plus 3x to the s equals 0. This and this cancel it. And now we separate where you have derivative x and x. Okay, minus 2x minus sx. I have minus 3s x to the s equal x prime to the s. We have factor s squared plus 3s. Okay. This means x prime to the s divided by x to the s. We have minus 3s over s squared plus 3s, or is equal minus 3s s over s plus 3. This is s and s cancelled. If you take it integral both sides, integral from derivative function divided by function is will be natural log from this function. Integral minus 3 over s plus 3 is will be minus 3 natural log s plus 3. Oh, I take x plus 3, but I write 3 plus 3. You see? S plus 3. And plus some constant, but you remember usually for this kind of situation we write like constant, like natural log from some number. And here we have x to the s, it will be a over s plus 3 to the cube. It means your function x c, it will be e to the negative 3c, because you have plus 3 multiplied by c squared, but because you have constant a, this means some constant c. We cannot find exact constant because we have our initial point, you have only value your function, not value your derivative your function, but here we have non-trivial solution. Okay, one more example, this type of equation. Now I clear. Okay. Clear, just a moment, sometimes it's take so much time. Okay. Question number 34 in your book. For section 4.4. Here we have cx second sometimes it's not work very well, plus 4c minus 2 times x to the first plus 13c minus 4 to the x equals 0, and here we have same value your function is 0 is 0. Here we separate little bit. We have cx to the second plus 4cx to the first plus 13cx, and then we have minus 2x to the prime minus 4x equals 0. It will be easy found derivative after. What you have first? For first cx square you have minus s square x to the s. This value your function, derivative your function is 0, and then we need found derivative minus 4s x to the s, and then you need found derivative plus 13x prime to the s. Oops, not plus, it's minus, because formula we have opposite sign. This means minus, and minus 2s x to the s and minus 4x to the s equals 0. Found all derivative. I have 2s x to the s minus s square x to the prime s minus 4s 4 okay minus 4x prime to the s minus 4s. Oh my god, 4 here's 4xs minus 4s x prime to the s minus 13x prime to the s 2s x to the s minus 4x to the s equals 0. Factoring the s, I have s square, then I have 4s, and then I have 13. Then we have plus xs, and will be, if we simplify, we have minus 4s minus 8 equals 0. This means x prime s over xs, we have minus 4 times s plus 2 over s squared plus 4s plus 13. Because denominator we cannot factor in, this means we can rewrite like sum two squares, and this will be minus 4 s plus 2, it will be s plus 2 square plus 9. Take it integral both sides, you have natural logarithm function xs, it will be minus twice natural logarithm s plus 2 square plus 9 plus natural logarithm a. This means our function xs, it will be a over s plus 2 square plus 9 and all of them square, and use inverse Laplace transformation for this kind of function. And remember what has happened, we have, it will be x from c, it will be c e exponent minus 2c multiplied by sine 3c minus 3c cosine 3c. Okay. We're done for today. Solving examples, solving your homework, and write question for me.